Yeah, so first I just want to show basic overview of what they are doing there. Yeah. So yesterday, let me see if I put everything in photos. Unfortunately, I didn't upload it from my camera, but I can upload it right now. Oh, I have it in my Facebook account, so I will show you. I will show you a video. Yeah, so here you can see. So here you can see how this event looked like. So they get bunch of students, and students came from so oh one second. I need to show. Yeah, yeah. So here you can see how this event looked like. So they got like many students from like Stanford, Berkeley, from UC. Sorry. Yeah. So they got like many students from Stanford, from Berkeley, from San Jose State, and most of students like already went through digital design classes, so went through Verilog. So they knew like already Verilog, and also there were people from some like government labs, from like Sandia labs. So if you look to my video, uh, so, yeah, yeah. So this is Matt Wen, who is the founder of TinyTapeout. Yeah, for example, this like a gentleman was from Sandia Lab, and they were yeah, but mostly they were students and researchers. So first Matt Van show some like videos and slides about like about semiconductor process, and then he let like everybody for half an hour to play uh, with this editor where you put like a polysilicon, and he like explained basic idea how a transistor works. So he put some slides about what is the mask and what is the transistor and so on. So this is like something good to know, but this actually has practically nothing to do with what like RTL uh, designer does. So and we are actually doing RTL design. So this like teaches physics of transistor, and he then explained how chips and how transistors are manufactured on a semiconductor foundry. So this is a course feedback. Yeah, that's it. So after explaining transistor, explaining transistor, so he put step by step, so you can actually do by yourselves the very same exercises he did like yesterday in Stanford. So he was saying that first you clean the whole thing, then you put like p substrate, then you uh, put like rectangle of metal and the via, and then you that you don't have error. So DRC error is just check that all like metal and silicon parts, they have like certain widths, and sorry, and then And then like he was showing how to check that the structure you draw actually works. So in order to check that the structure you draw actually works, you create a new signal and you press a simulation button, and then like it simulates here. And then he was showing how the photography process is done on a foundry. So if you go to this website, you can pretty much get all part from this lecture. Yeah, and so then second thing, what he was doing here, he wanted to use editor called Wokvi, and so what this editor does in this editor Wokvi. Yeah, so what this editor Wokvi does is it essentially allow you to do schematic entry. You can get his pre-made design which corresponds to his board, and in this pre-made design he has like a source of clock which is either from a button. Opa. No, you have to press simulate. So then you press this step from a button, but in order for this to work, you need to connect this wire to this like clock wire. Uh, yeah, I cannot do this while I'm in Zoom, but like basically you can like add like different gates to this editor. So you can say that like I can add NOT gate, AND gate, OR gate, and XOR gate, a multiplexer, and D flip-flop. So those are components. So you can add them here, and then you can move this buttons around. I don't know why it doesn't let me to move this button, but yeah, this editor is not very convenient. Yeah, let's connect this wire to here, and let's remove wire from here. Oh, sorry. So let's connect this wire to here. Hi. Yeah, so basically I'm now just giving some like overview about a class which was yesterday in Stanford. So there was like a TinyTapeout class, and like Matt Van was showing what was in this class. So yeah, so they were. What's it? Did you go there or? Yeah, okay. So like basically, first he was showing some like basic editor of like silicon layers to build a transistor, and then he shows this schematic editor called Wokvi, how to draw schematics diagram and how to simulate action. And then in this action, you can run clock, you can turn on and off buttons. Uh, so you can like turn on and off buttons, and you can build some like structures here. So you can stop the simulation, and then you can add, let's say, like a flip-flop. So here is like a flip-flop with the reset. So yeah, unfortunately it doesn't work when I share with Zoom. So let me stop sharing, and let me just do it like without sharing. So you can, for example, put here flip-flop, and you can get this clock, and connect this clock to, let's say, here, and then you need to. So let's this wire, let's remove it. Yeah, this editor is not very convenient. So you need to remove this wire. So you need to remove this wire, and you need to connect clock to, let's say, here, and if you connect clock to here, what you can do, you can simulate, and you can press this button, and you can see a clock signal connected there, or you can press this button 10K, but in this case it will blink too fast. Yeah, and you can so you can connect this clock wire to, let's say, our D flip-flop, and like run various exercises. So now let me share screen again. Yeah, so basically here Matt Van intentionally didn't want to like introduce people to Verilog during his training. He just wanted to make such schematics, and then to submit this schematics for the manufacturing to Tiny to Tapeout, so that after like 6 or 7 months they're getting chip which has like their own design. And for people who are not familiar with the Verilog, this is like good introduction to the process. I personally feel that moving wires here is more confusing than just simply do this on the breadboard. But this is like a viable option to teach schematic entry. So then after he put static entry, he was showing how to use web, so how to use GitHub on the web, so without even cloning repo, to submit his design for manufacturing. By the way, there is half an hour. You still do this until 24 minutes. You can still do this until noon. So actually, if you're fast enough, you can submit design, and this can be manufactured until noon. So they are doing a submission like every quarter. So you can actually prototype something on FPGA and then submit and have your own chip. And this is actually good for like you, because you can use it as something you can show for like entering some universities that like I made my own chip using this process. Yeah, so basically in order to do this, you need to get a template. One second, let me. Yeah. So in order to do this, you need to go to GitHub, and on GitHub you need to get template, and so he was asking everybody in the room to get this walkthrough template, and then he was asking to like enable GitHub action. So what GitHub action does, when you have basically he is running EDA software on the servers, and the GitHub action is the way to like enable running this when you check in your own design. So you like modify this design and you check it. And now in order to make this design manufactured, you need to modify YAML file, so just a text file which contains information about like title of the design, including like author and the description, and all this description is compiled in the documentation. So what he manufacturer, he actually sends to like everybody document with documentation about this thing. Now, how your design is connected to like outside world. So you have 24 pins. So some of these pins, 8 pins are for like input only, 8 pins are for like output only, and there are like 8 by directional pins which you can use to like either for input or like output. And now you need to enter this information. Then you need to upload this workview design, and then the kit will automatically puts this design into GDS file. So GDS file is a file which has like geometrical figures, which we discussed in here. So like GDS file is a text file which has information about such like polygons, so about like rectangles of metal and polysilicon and everything else. And we are like essentially sent this GDS file to the Silicon Foundry. Now he instructed everybody to submit design, and you can still submit design by like within the next like 20 minutes. So what you do is that you create a new project and you fill this form on a website, and you put like your name, your email, and you put your repository in a GitHub, and it will manufacture a chip based on your design. So yeah, and this was like pretty much it. So now let me see if I have this in my Google Photos. So I will show you everything, like everything from this meeting. Just a second. Oh no, this is the wrong account. This is the right account. Yeah. So oh, but actually it didn't load yet. Yeah, once it finishes uploading, I will show you photo pictures on like during this thing. Okay, so let's go back to yeah. Yeah, I will send the information about this event. So now let me show you TinyTapeout design of our examples I did. Because what I was proposing to Matt Van, so like I told him, so let's actually make a joint hackathon where we first prototype designs using FPGA boards. So we just use FPGA boards, and then we put the very same design to like ASIC using TinyTapeout. So I will probably discuss over Zoom this with Matt Van, but even if he is not particularly interested. So first of all, my overall impression is that he is not interested in training engineers for the industry. He is most interested in just giving everybody like some like insight what is going on in a silicon manufacturing. But his infrastructure is actually very convenient for training engineers as well, because he has complete open lane underneath, and you can see like static timing analysis reports, and you can see produce GDS files. So this is very efficient for like our examples. But he also he like allowed to do coding in system Verilog. So let me show you my own design with his infrastructure. So I put 3 of designs we are doing as projects with a TinyTapeout. So one of this design is a C battle VGA game. So like remember, this is the game on LCD screen I was showing, right? And in order to create your own project, first you're going to a TinyTapeout website. So you're going to like TinyTapeout website, and you are getting TT09 Verilog template, and you click here on a button called use this template, and that will create uh, your own. So for some reason it doesn't let me in Zoom to press it. Anyway, uh, but you create your own repository, and I'll show you how my repository, which I created 2 months ago, look like. So in this repository, it has instruction. So in this, what you need to do is that first you need to modify a file called YAML, like info YAML, where you put like a title, your name, your description, language system Verilog. Then you put clock frequency. So like I put here 23 megahertz because this is the clock frequency of lower than VGA. And then tile, so how many tile you use. So each tile allow you to put approximately 1,000 logic gates or like diff flip-flops. And to build a like RISC-V CPU, like 32-bit CPU, you need like at least 1024K bits for register file because I have 32 registers by 32 registers. So if you want to build even the smallest CPU, you need two tiles. Unless you want to do CPU not RISC-V but something else. But still, what they offer is enough to build your own microcontroller size CPU, especially if you buy more tiles. So you can actually build real design with this thing. You know, you don't need to like restrict yourself to like toying with thing how he was doing like on seminars like yesterday. Yeah, now you need to specify top module, and then you need to specify source files. And source files are the very same source files used for FPGA. And then you need to specify pinout. And their like interface is very narrow, so they like allow to use only 8 pins for input, 8 pins for like output, and 8 pins both sides. So what I did here is that I connected one key which we use on FPGA board to their signal UI0. So key right, key left, and then I put pins for VGA, for like RGB VGA, and for VSync and async. So for VGA we need like I say minimum 8 pins. Okay. So then, in addition to this file, what else you have to do? You have to put all your source code. Okay, then you have docs. In this doc, this doc is created in a MD format. So for those of you who don't know what is the what MD format, so there is uh, there is like a lot of materials on the web. So MD format. So this is a markdown. So this is markdown guide. So you're going to a website called Markdown Guide, and basically MD format is just a text file, which is functionally equivalent to a subset of HTML file, but it's written in a form that you don't need to put a bunch of like brackets. So, and you can actually read this MD file just as like any a text file. And this is the way how TinyTapeout makes a documentation. So now, so now, if you go back to my example project, and here, see it's Flutter. So you can see that it produces some formatted text you can read. But if you press here row, you can see how this looks as a raw text file. And you can see that as a raw text file, in order to make such formatting, you put this like number sign to make like a large title. You put a star to make it bold, and you can incorporate HTML links in the following format. So once you do this, text file formatted in this way is actually can be used instead of like a Word format or like RTF format. So this is just a reliable, portable way to write a documentation, which is also web friendly. So here I put descriptions. The C button is the game and like all the color code and how to test it. So test need to connect VGA connector. So now, one thing which I don't like about TinyTapeout is that they like to use Python CocoaDB as a test. And Python CocoaDB, there are many people who are big fans of Python CocoaDB. So CocoaDB is a library in Python which simulates, which has the same like functionality as System Verilog. But because it's in Python, people who know Python can use it instead of System Verilog test bench. And I mean, this is like great, and it allowed to do the same things. So it allowed to put like Python code. You put like import CocoaDB, and then you say that when test starts, you create clock, then you start clock, and then you set some signals, and then you wait for certain events. But the problem is that CocoaDB is not really used in industry because it's very slow. So basically, when we do like GPU in Samsung, we have to run giant tests, which runs like many hours. People in Cadence have tests for CPU, which run for like several days, like 5 days to run tests. And if you put the Python instead of System Verilog, the whole thing will run like not like 5 days, but like half a year or something. So this will be everything slower, you know.
File down to System Verilog.
Essentially, this is a wrapper over System Verilog. So they do call System Verilog using a DPI interface. So some people claim that because they use DPI, if you put just a little bit of Python, it will not be that slow. But I didn't experimentally tested it. You can actually try and like tested it, but and for those people who start from like Python, this is good thing. But the problem is then if they like interview in industry as a verification engineer, if they go to like job interview in like Apple, Nvidia, Samsung, and so on, they will be asked questions about System Verilog because CocoaDB, I don't know a large semiconductor company which is using CocoaDB right now. So maybe they have somewhere, but the thing is that I I'm okay about offering CocoaDB as an option, but offering CocoaDB as a single option, I'm actually not okay with it. So I was trying to work around it here. So if you go to the CocoaDB, if you go to CocoaDB website, it's a Python verification framework. They may have claims about Yeah, so since provides CocoaDB project is VCS license for integration testing, okay, but this is a tool vendor company, so they are interested to make themselves compatible. So now like Aldec, Cadence, those are all tool companies and tool organizations. So they want to be compatible, but you see, they don't have links to large electronic companies who like endorsing. So for this reason, what I did, because I didn't want um, to learn like CocoaDB and to spread CocoaDB knowledge around, because then you cannot use it on the job. So what I did, I created a rudimentary test bench, which just in a Python CocoaDB, which just waits, we just okay, so we wait here clock cycles, GUT clock, yeah, wait for one clock cycle. Okay, did I put it here? Actually, in this project, I didn't put anything meaningful into testing. I have another project where I put something meaningful, and this project is a CPU. I put it in organization DDVCA just because I did some seminars in Central Asia. I created this organization and digital design and verification Central Asia, and I put some projects here. So here I put with the CPU, and what I did in this testing, I put a test in Python, which starts running clock and put initial values to signals, but then it just wait for 300 clock cycles and then checks whether test pass by accessing signal in system Verilog design. So like essentially what I do in this like Python code, I just say that, okay, let's run clock, let's set initial values to the signals, then let's run it for 300 clock cycles, and then at the very end, we just like at the very end, we just check whether whatever we run like actually succeeded. And if it didn't succeed, and success we get from system Verilog. And if it didn't succeed, we are doing assertion in Python. And this assertion is intercepted by a testing code in TinyTapeout, and they figure out whether test pass or not. So this like testing is not really needed for TinyTapeout. This testing is needed for us to make sure that we didn't produce something which is manufactured and we found 7 months later that it doesn't work. Okay. Now, so what is next in this design? Okay, so this is what we have in a test directory. So in test directory, I also put test. Let's actually see it in my for CPU, because for CPU it's I made it better. Let's turn off this one. Yeah, so here also it has a readme and has like edit make file to modify project sources and edit a test bench tb.v. So here is a tb.v, in this like tb.v. So they provide both Python code and a rudimentary system Verilog test bench where they just instantiate design and where they put like a module for the design, and that's it. So they don't do anything after this. So I kept their rudimentary design. Then they have makefile, and in this makefile you need to put all your source code, and yeah, and like modify modify wake file. Then there is a requirement doc.txt. It's their own file. I didn't change it. So it says that a version of PyTest and CocoaTB. Then you can also put here GTK wave, so waveform you expect from this thing. And yeah, and that's it. So those are just some yeah, so our main thing is in the directory called src. So inside src, we are putting source code. So if you go back to C battle, inside src, I put all from our FPGA example. So like I put all source file from FPGA examples. But in addition to it, you also need to put a file called project.sv, which is their top module. So in their top module, they have certain interface, and this interface which you cannot modify. So you cannot modify this code. So this is something just bottleneck interface, and you need to squeeze all your signals through this interface. So there are some like inputs and some outputs, and 1 second, I have to fix this. Okay, this is yeah. Okay, can you hear me? Yeah, can you check? Can somebody check if they can hear me? Yeah, George, can you check your sound? Okay, good. Okay, yeah, okay, yeah, you can hear me. So, so now, uh, this interface is like narrow, so we need to instead of our like Verilog top, we need to put all signals through this interface. So they have clock, they have reset, they have enable, which we can ignore. This is always one when design is the power, and they have input and output pins. So for our C battle game, I just assume that I'm getting left button from UI in 1 and right button from UI in 0. So two buttons. And then I put signals for H-sync, V-sync, and red, green, and blue. So standard buttons for a minimum VGA display. And then I instantiate this game together with the VGA controller and connect pins for red, green, blue, V-sync. So here, like I put actually two channel, red, green, blue. So like two bits per channel. So we can have here more interesting colors. In principle, you can use only 5 pins, just RGB, H-sync, V-sync, and that's it. Yeah, now, yeah, and this is files you need to pick here. And now kind of interesting part. So now, if you go to, so now I want to show you how it runs behind the scene, how it runs the actions. So you see, it has the action to generate GDS file, to generate documentation, to generate a test. So you need to go here to a place called actions, and this run behind the scene automatically. So every time you are doing check in and push into GitHub repository, it does 3 things. It does testing with our website. It produces documentation, and it produces GDS. GDS is a file which goes to semiconductor foundry. So first of all, let's see what it does with the documentation. So when you look into results for this documentation, you can go to docs, and you can wait. Yeah, so you can see that it produces artifact, and this artifact is a PDF file. So you can simply download this like PDF file. Yeah. So and now you can go to a directory, to your download directory. Wait a second. Can you actually see it here? No, you cannot. So you need to go to download directory, and you need to get okay. TT submission. Yeah, here is the PDF. So let's just extract it here. So where did it extract the file? PDF zip. Yeah, datasheet. Yeah, datasheet.pdf. So you can see that it produced documentation from .md file. Yeah, and the in .md file you can specify even table, but in order to specify table in .md file, let's go back to documentation.
How was that generated that documentation? You did it, or it's that documentation was generated by you, or it's
This documentation is generated automatically by the action process running on server, which is set up by TinyTapeout based on this text file in MD format. So you basically write MD format as a text file. It's a markdown format, and then it generates nicely formatted documentation. And I can show you how it. And their like software running on this action server also appends to your document table with the pins, and this table you specify in a YAML file. You see? So yeah, so one artifact you're getting artifact which is a documentation in this MD format. Now, if you go back to actions, so they have docs. All close. Yeah. So now they have step called test, and in the step test, it's running our test bench. So as a result of running our test bench, it generates VCD file. So VCD file is a waveform. We can use GTK wave to see this waveform. So if you go to let me actually do this in terminal to be faster. So if you go to download, and if you go to test yeah, so test VCD. So if you go to test VCD, it produces tb.vcd, and you can use either GTK wave and which is a viewer like this. Then what you do is that you go to test bench, user project, and in this user project you can see you can append your signals here, and then you see what is going on. But because
that is screenshot not shared. That one's are not shared.
yeah, let me share it. Let me share it to Zoom. Yeah. So let's do share the whole desktop. Yeah. So you download this file, then you run test. But because in our test here we are not doing anything, this test is not interesting. So let's get another test. So let's get test for CPU. So test for CPU. 1 second. It's somewhere. Yeah, it was GD GD design C repositories. Yeah, let me show you this artifacts from CPU test, because it's just more interesting test there. Yeah, so if you go here to actions, and then if you go to test, and if in this test you download artifact, which is test.vcd. Yeah, so if you download artifact, it has this test vcd. Yeah, so this has tb.vcd and results XML. So here's our results XML. So in results XML, it put a random seed. And this random seed, I think it's a part of Coco TB. So this random seed is necessary to reproduce our results, not in their web-based infrastructure, but is our infrastructure if you want to run it locally. Yeah. Now, if you look to TB VCD, we can do GTK wave and a file name. So we can see it. You can see it on the screen. So we can use user project, and this user project. So first we can get signals from a test bench. Yeah, so you see this like project is more interesting. We can actually see CPU signals here. So in our test bench, we simply instantiate raw signals which go like outside of chip to like buttons and LED. Yeah, so let's remove the signals, and I can show you what it corresponds to things in our code. So if you go back to the code, you can see signals on the test bench. So this is a test, and we have here test bench. And in this test bench, it simply instantiates our design. So those are signals from their test bench. Now, if we add to GTK wave user project, those are signals we have on level of project.sv. Yeah, so on level of a project.sv, it's a file which we put in SRC, and in SRC we put a file called project.sv. Yeah, so this project.sv, we essentially making interface between their pins and our CPU core. So our CPU, not core, like our module called the SoC, so system on chip. So we So like I decided to put outside only current value of program counter and the current value of register A0, which is one of RISC-V CPU registers. So like essentially everything which is memory and CPU core are inside the system on chip. Yeah. So now next signals we have here is signals in our SoC, and those are signals. So we have inside module. So if you go to source directory, it has a CPU core which computes Fibonacci numbers, and there is a module called soc.sv, which has as inputs clock, reset, and like as outputs program counter and 4 bits register A0. And also it has bits pass and fail. And this is exactly the fail we are checking in our Python code. So here we create module for a CPU, and then we created module for instruction memory, and we connect them together. So you can see on our waveform that we run clock, and then we run reset, and then we have instruction memory address, instruction memory data. So we are fetching instructions from the memory. So this address is 0, 1, 2, 3, 4, 5, 6, 7, 8, and then it goes into loop. So then we start looping those instruction. Yeah, it's here like 8. Yeah, 8, 9, A, B, 8, 9, A, B. So this is the loop. Yeah, and this counter is just a counter which counts clock cycles. Yeah, and now we are fetching instructions, CPU instructions from the memory, and then we decode them in CPU. And eventually we have a signal called pass, which tells us that we pass the test, and that's it. So we pass the test when we see certain Fibonacci number on the like in the register. When we see certain Fibonacci number, we see that we pass this test. And then we also look what we have on our registers, and we compute Fibonacci number on register A0. So we can see it on the waveform. Yeah. So basically, if you go back to the code, you can see that we have CPU module, we have instruction memory module, and we have signals, and we see those signals on the wave. Now, like if you dig deeper, you can see that in CPU we have like decoder module, program counter, and so on and so on. And in instruction memory module, we simply use some trick. We simply put instructions because YOSIS cannot process this read mem page. I had to put these assignments explicitly. So I explicitly put all instructions from a Fibonacci number assembly program as just assignments to this array of wires. So this is how like testing in this infrastructure look like. Now, most recently, I actually stopped using GTK Wave, and instead of GTK Wave, I started to use another program called Surfer. So like 2 weeks ago, but once people switch to Surfer, they like abandon GTK Wave. So syntax is same. So Surfer TB VCD. Oh, let's do wait. Sudo apt get install Surfer. I'm not sure whether it No, it doesn't have surfer here. Anyway, we can install. We can actually install surfer in Visual Studio Code. So if you go to plugins, if you go to view plugins, so where to put plugins? Like I just put Explorer. Wait just a second. I just want to put Surfer plugin so you can see it. You can see it in the VS Code. Okay, let's minimize terminal. So where is the selection terminal? Okay, I need to get the plugin. Yeah, view, open your appearance, secondary sidebar, center editor layout, explore, search, source, yeah, extension. Yeah, here is extension. So there is extension called Surfer. Yeah, this is extensible and snapper waveform viewer. So we just install Surfer, and we will see Surfer inside VS Code. It's installing, takes some time. Yeah, so this okay, is it installed? Yeah, this is installed. Okay, so now if we go to okay, how to close this thing? View. How to close this window? View. Control Shift X. Yeah. Control Shift X. Yes. Yes. I'm just just trying to close this window. Yeah, explore. Okay, good. Okay, so now if we open, let's say, if you open our folder downloads, and if we click on if you click on our recent tb.vcd, yeah, so you can see this in Surfer. So what you see in Surfer, you can click on TB, you can click on user project, you can click CPU, and you can add CPU variables. So let's put clock. So you see it adds clock. Then let's put a reset. Then we add program counter, and then we add then we can go to like SOC level, and then SOC level we can add instruction address, instruction data, program counter, register header, I mean register address. So we put a value of register A0. So this data we don't need, and this we don't need. So now yeah. So now you just go here, and you can like zoom it. So you can zoom inside, and you can see like current. So same thing what you do in the GTK wave, but just a little bit more features and just a little bit more convenient. So you can like move with mouse this waveforms. So you can scroll in this way. So yeah, so Surfer is certainly better waveform viewer than GTK wave, but essentially they're doing the same thing. There are also some professional some waveform viewers we are using in the company like Verdi or SimVision from Synopsys and from Cadence, and they like allow to also do such operations as looking for drivers for a signal, so where value of signal came from. Yeah, but let's go back to the most interesting part of this whole thing. The most interesting part is to get GDS2 file. So let's see GDS2. Huh?
The sharing screen is frozen.
Really? Just a second. Stop share. Yes, so let's share on desktop. Okay, so you can see. Okay, so now let's go to the most interesting part of this thing. Let's go to watching GDS2 file. So, yeah. So the most important thing is the GDS file is a file which is going to semiconductor foundry. And you can see that here, when you click on GDS action, so when you click on GDS action, Zoom does not. Yeah. Okay. So when you click here, you can see that this GDS action has the multiple sub actions. So it has the GDS viewer, pre-check, and so on. And this gives you a lot of interesting information. Like it shows you utilization of tiles, so how much chip area was used, and then it has the cell usage by category. So it was saying that types of cells which were used, like and with 2 inputs and or and flip flop. So it was using 306 bits of flip flops. It uses a number of multiplexers. So it was using totally of 1739 cells. So, and basically one tire is a 2000 standard cell. And each standard cell is like either logic gate or some D flip flop. So now you can use that it passed the based pre-check test on physical level, and now we want to see GDS rendering. So now it does also gate level VCD dump, which is also very for. But this is the coolest part. The coolest part is GDS rendering.
If you get more than 2000 cells, it expands automatically to use 2 dice, or
no, you need to like order, because each 1000 cell costs $50.
okay.
So if you want to make like some serious thing, you need to like buy them. Yeah, but even in 1000 standard cells, you can put interesting non-trivial exercises. You can put like some like job interview type of questions in there easily. And if you have like 20,000 standard cells, you can put a microprocessor which can run Linux in there. So actually, it's not that small amounts we are talking about. Okay, so now let's see to GDS render. So GDS render, you can see a 3D image of what we. No, this is actually PNG, but you can run. You can run. You can run here. You can run here a program. So okay, show the files. So in this GDS render, So just extract it here. Okay, so let's see GDS render PNG. So this is like a flat image of our design we created. Oh wait, it's a frozen there again. Let's stop share. Let's share screen. Let's share this GDS render. Yeah. So and you can actually zoom in. So zoom in, Control Shift. Yeah. So you can actually zoom in and you can see your cells. You can see your cells on a chip. So you can see your cells on a chip. But they have also 3D program where you can see a 3D image. So let's run their GDS viewer and see 3D image. So okay, so this is GDS render, GitHub pages, check report, gate level. Okay, let's see, viewer summary, yeah, load summary. Yeah, they have some way of loading and CS3. Yeah, here viewer. So we went through pre-check. We went through.
You're not sharing again.
Okay. Yeah, so you can go to pre-check. Okay, GL test viewer. I'm just trying to find a program. They have a program that allow to see a 3D image of this whole thing. Your summary artifact. Yeah, so GDS test VCD, TT submission. Let's see, maybe there is the NTT submission. Test GDS logs. Yeah, and in the GDS logs, you can see static timing analysis reports. So like everything else in like as in an electronic company. So let's see, TT submission. So what is inside TT submission? Oh yeah, so this is doc source. No, this is what goes to the file. So open. Yeah, I don't remember how I did it. Okay, test VCD. This test VCD. I don't remember how I did it, but they had a way how to show 3D 3D rendering. Yeah, so I can see now only PNG. Yeah, maybe so they have a special interface which allow to like rotate and see this in 3D shape, which is actually very cool because you can see like transistors in 3D. If you go to LinkedIn, I actually made a picture. I made a picture I created using this program, but I don't remember how I did it right now. Okay, so let's see. Yeah. So you see, you can have a 3D image like this, which you can rotate and you can see like zoom, you can see internal 3D transistor structure and so on. I mean, it doesn't really have like any like a practical meaning for like us as software designers, but it's like cool to see on the screen. Huh? Yeah. Now, okay, so now like I show what this like tiny tape out is, and then I put a then I'm going to put a proposal. In fact, I want to send this proposal tomorrow. So I want to send a proposal to eFabless. So like my basic impression, I don't think that like Matt Van is particularly interested in mixing like ASIC and FPGA because I think based from our yesterday action, you can correct me if I'm wrong. So his goal is to more to show it to general people, get feeling what is inside the thing, but he does not have intention to train people how to do design, like on very low level. Yeah.
He was very much in showing what the capability that you can do with all things to give you a full idea.
Yeah, this is kind of full idea, but what? So let me show the proposal I'm going to put there. So if you go to Verilog Meetup website, so you go to if you go to some recent thing, so I put that. So we are working on a hackathon proposal, and this is what I want to propose to eFabless and to Gorin. And actually, Gorin, they are interested to help us doing this. With eFabless, I chat with their founder, with Maker Fair, but I need to follow up with him. So in addition to this workshop proposal, we're working with hackathon proposal in which the participants prototype graphical games on Go and FPGA boards, then present games to panel of judges and gamers, and then finally implement using TinyTapeout and eFabless. But still I didn't show a report. Still I didn't show a report from synthesis report. I still want to see synthesis report, because here you can actually show static timing analysis report somewhere. Job summary generated at runtime. No, it's not it. Just to help. So somewhere here they have GDS logs. Yeah, you got GDS logs. Let's see them before we switch to this different topic, because in GDS logs they're supposed to show static timing analysis.
What's the process technology?
This is 130 nanometer. Yeah, so this is same process technology which is still used for some microcontrollers. Yeah, and this is good enough for education. Yeah, so now I'll read. Oh my God. The big log. 1 second. Yeah, runs SRC. So he is the source, and he is yeah. So you see, oh great. This is actually how people can be educated. So you see, if you download their logs, you can see their report for every single step. So they go into Verilog and yeah, flow logs. So they put the whole like open lane log, how they run all different steps, including like static timing analysis. And so they have like so they have final static timing analysis report. So if you go to, let's say, okay, this is so you can see like I think this floor plan definition. You can see GDS file, but it's a binary file, so you cannot really see it. Maybe we can see it with the magic viewer, because we do have magic viewer. Okay, so you can see it in a synthesized Verilog, where it's represented as a bunch of sky water cells. So you can okay, place a route is okay, SDC. So what do they have? Yeah, those are delay specifications, SDF. Oh, this is no, this is SDF fast. I'm just looking for their reports. Which okay, let's see. Static timing analysis report. STM.
Is there like a target clock speed?
This is not like target clock speed. We set target clock speed. This just shows critical path. So the combination are part of design. All the delays, so like ends, ors, and so on. The whole path. This is what I'm. That's what I'm. But it can show maximum clock speed. This design can do, or it can show negative slack. Just I want to see report first. Okay. Open road STM. Okay, DRC manufacturer. Okay, open generate. Yeah. So they have reports. So let's actually find all reports they generate. RPT. Yeah. So they have bunch of reports. Oh, they have summary report. They have summary report and the QNR. Okay. Large okay, checks, VS means, Q mean report, max. So do they have anything QNR report? Oh, CT. Okay, let's see. Checks. Yes, anyway, I will find those reports because, oh, here's a summary report. Let's see this one.
There's TNS max.
Yeah. Maybe there. So let's see. Where is it? Yeah, here, TNS max, TNX mean report. Yeah, so such tools produce like tons of such reports. Yeah, you see, so this is what we are looking for. We are looking for worst slack, and the slack should not be negative. And I guess so. We got already area report. So what is slack? So let me say a couple words about what is slack. So when we have like, let's say, like clock cycle. So like when we have like clock cycle, and during this clock cycle we compute something. So you compute like and or, and each and or has some delay. So by certain time, when we finish of computation, we have some stable result of computation. Okay. And basically, if we cannot compute like everything within clock cycle, then we like violate a timing discipline. So slack is actually a difference in a picosecond between how much space we have between the next positive clock edge. So we start computing and we compute during this time, but slack is the time which is left. Now, if our computation does not fit into clock cycle, then slack became negative. So basically, our goal as RTR engineer is that this number should never go negative. Yeah, and if it's negative, then we need to like, yeah, so this is summary report. So let's see if you have some more summary report, or if you have anything is called QNR, which is quality of result. So let's see, find name, find dot name star Q quality of results. So whether they have report? No, they don't. So, but they do have. Okay, what about area report? But area report we saw it already. So we have so that thing was called a summary, right? So let's see whether you have any more summary. Oh, we have actually multiple summary reports. So, but we have antenna summary, regular summary, stop pre-PNR. PNR means place and route. So STA, static timing analysis, post-PNR, and static timing analysis pre-PNR. So those are reports we need to check for our purposes. And open, yeah, so everything else is antenna. Yeah, so those are two reports we have. Everything else we get from the website. So website tells us how many cells, how many like and or and so on cells we use for our design. And this table tells us worst slack, and all our slacks is positive, which means that we compute everything in clock cycle and still have time to compute anything more. Yeah. So this is practically all we care. So we care about area, we care about static timing analysis for like our exercise. So now let's go back to like our proposal. So if we go back to proposal, basically we want people like all of you to create some like cool games. So the first of all, game should be like interesting, but game should also be properly running on FPGA board and should satisfy area and static timing analysis requirements for the for eFabless. So in order for this chip to be manufactured, so we essentially manufacture small game machine on a semiconductor foundry. And so those people who participate in this exercise, they first they first play with FPGA boards, and then they play to the degree they can create interesting game, and then they show it to like panel of judges, and then those people who created something interesting, they can get as a prize, they can get to manufacture their design on a semiconductor foundry. So and since the simplest possible, I mean like, and if the only restriction is I don't want people to create game machines using CPU cores, because if you have like a processor core, what they can do is that they can simply download from internet ready-made design of Nintendo, put it into FPGA boards and load of Nintendo game from 80s and claim that they created the best game in town. You know, this is something I don't want them to do. So this is like can be like a workaround, and so they don't show that they are designers, but they show instead that they are like you know. So yeah, so this is my general proposal, and this is what I want to send tomorrow to people in eFabless and CC to Govin and to Matt Van. Like I don't think that Matt Van will be much interested, because he was saying that we have already this one demo scope. So if you go to TinyTapeout, the TinyTapeout website, you can see that they have competition demo scene. So in competition with in demo scene, they are competing on making this like graphical designs. Yeah. So in this competition demo scene, they are competing, but the problem is that you can see this this graphics only either in simulation or 7 months after you get your chip from the foundry. So you don't have like interactivity right now. Yeah. And we are doing interactivity by putting FPGAs. So now like Jan probably didn't see those sets. This is something I want you to play with it today too. But basically, yeah. So Jorge, what do you think about this proposal generally? So let me get sets, and I will let everybody play with such thing.
It would be very nice to have some kind of game.
Yeah. So we just play with a bunch of games. So now, did you see like this set or not? Yeah, okay. Now like I will show you how to do this, and we will go with you through like basic training in how to do this. So what kind of computer do you have?
Windows or
Yeah, you can install necessary software, but you can do this later on. So now I will just give you another computer. I have like a bunch of computers you can just loan from me. And actually, I just bought on eBay like 7 cheap laptops. So I can actually, if you do a thing in Mexico, I can just bring them with me. So they, even if they completely mess up with their setup, we have like 10 computers of our own. Yeah. So now this is the setup, and now I will instruct you how to work with it. I will give you a computer for this. Just a moment. And you know test setup we will use in Mexico. So just a moment. Let me give you that computer. So Jorge, do you have already date for Mexico or not yet?
in the conversations with Enrique and the people back at
What? Okay, yeah. So now let me give everybody this set, and now we will actually do this graphical game right now. Just a moment. I need to find where is my another. Okay, so now I want everybody to get. So I want now everybody to get some computer and start with it. Have actually short ones, so I have 3 of them. Okay, so this is our demo machine for so this is our complete setup for Mexico. I'm going to get like I got like 7 of this, plus I have three like another one. So let's plug it here in. So now we test the whole idea on Ariana, and I have one more computer. So let's connect it here. Okay, and this one you connected here. So you connect it here. So now you just open it, that runs Linux. So just like connect it here. Good. So now you just look and follow. So this starts Linux. Okay, now next. So I have one more computer. So you have computer. Okay, so just a second. Okay, so yeah, you have this computer. So do you need the computer? I have one more laptop.
I already have one.
Yeah, you have. So you can set it up. So like you mean computer where you connect monitor? So you can connect monitor and do this as well. So do you have this thing set up on your computer?
Yeah.
Okay. Yeah. So you can sit here and you can in fact help. And you can help Ariana do this. Now I have. Let me get couple more sets, and now we will. And now we will start doing this exercise with our sets. Just a moment. Let me get it. Okay, but are there any questions about the stuff I show about a TinyTapeout? Oh, I have a couple more sets. Okay, so you have your set. So who like that? You have? You have. So do we need any set? So do you have your set? Yeah, you have your set. Okay, so like everybody set, right? Okay, so now I will show to Ariana how to run the thing. So I will put a set here. Yeah. So now the goal of today is to create some graphical game. Yeah, we will not even connect TM1638. We will just use a two button version of a game. So correct. So basically, for the planning, the best time would be to do this in Thanksgiving, because in Thanksgiving it's kind of easy for me when if I could take vacation. So Thanksgiving is like easy. Yeah. Then I think that for dates during Christmas, it's probably not convenient for them to celebrate. Yeah. And so like if you cannot do this in Thanksgiving, you can do this in January, like up to them. Yes. So you're essentially waiting for the proposal about dates from the university. Okay. Yeah. Okay, good. So now, okay, so now let's close all these tiny tape out things. Let me see. Now, one important thing. Ariana, you probably already saw it, and if you didn't see it, I can show a couple of. There was another guy who. There was another participant, but he probably. Huh?
So this project is continue of last, right? Or
Yeah. This is the continual cluster. Yes.
Windows,
Huh?
it doesn't have a Windows platform, right? So we'll do the Linux.
Yeah. He can just connect Linux. This is called run on the Linux. Yeah.
Or the
He doesn't need Windows. He can run everything on the Linux.
Linux.
Yeah. So he just connects that like SSD and it just runs Linux.
What about at
Huh?
What about at home?
Oh, but he can use the same setup at home.
Oh,
Yeah, because this is what they gave. Because the gave.
the Windows laptop, but we don't have a Windows.
I know, but you don't need Windows. If you have monitor at home, you just connect monitor to the thing.
But he need to pull out the clone the workspace, right?
No, he can pull clone like on the Linux as well.
Oh, from this.
Yes. He can do everything here. He doesn't need Windows at all. Yeah, so like as long as you have monitor and keyboard and mouse at home, I can show how he can do git pull. Yeah.
That'd be good. So
Yeah.
yeah, he was looking for a Windows laptop. We don't have one, so he
Yeah.
couldn't do anything.
But no, this is fine. I can show like everything here. Yeah. So let's just so you can just get monitor from there. Yeah.
Julie, do you think it's a good idea today to put the slide to Spanish?
Slides, if you want to, yeah, absolutely.
Hey, can you give me access to them?
Yeah. So let me share to you. Yeah, I think I will create some special version of slides, special for them.
Yep.
I will combine and give you, and then you can translate. I think that if they decide like tomorrow to do some Thanksgiving, you have 1 week for it. If they decide to do in January, we have more time. Yeah. Yeah.
Oh, is that?
Yeah. Okay. So you can connect. Huh?
Looking for a virtual machine.
He want to put virtual machine. Well, I am not sure whether virtual machine will work with the software. Maybe yes or maybe no. Yeah.
Windows have the, but not other.
Yeah, but you don't need Windows for it. In fact, Linux runs with this much better. Plus, everybody, like every designer, like large electronic companies use for this things Linux. So nobody uses Windows for this. Yeah. So like practically, you can just get that like monitor and try it there. Yeah. Or if you want Windows laptop, I have that Windows laptop. Yeah. So actually, just a second.
Oh, for.
Oh, yeah.
Yeah, I have actually Windows laptop if he wants.
Because, it's, yeah.
Yeah.
Yeah, if you want, you can use Windows laptop right now. Yeah.
Later on, I'm guessing OpenFPG is already installed on this laptop, right? OpenFPG is already installed.
Yes, this is installed, but in order to use it, if you want to use OpenFPGA, you need to do CD to okay. Oh, wait a second. What are you trying to do?
We're trying to run red rectangle or like
Just a
upload it.
second. One second. Did you choose a FPGA board?
Oh, maybe not.
Let's check. So first of all, let's get mouse. Just a second. I will give you a mouse. Additional one. Yeah, let's get additional mouse so that we can easier. So I just want to see what board is used here.
I don't know.
Yeah, currently Sexton Nanos uses. Yeah. So Yosis
I think he's
Yosis is here, but I don't want you to use Yosis right now. Yeah, because Yosis is more.
Yeah.
I will give you a hub in just yeah, let me find hub. But so what you need to do here, you need first to choose another FPGA board, and then after you choose another FPGA board, you choose number 60. Tank down KCD for 80 to 72 so number 60. Yeah, number 60. Okay, so now Oh.
Yep.
Okay.
I listen.
Yeah. Can you hear now? Okay. So this was just like recently disconnected, right?
Yes.
Okay, this is fine. This cable is not. Yeah. Okay. Now. So now you have so what is the yes, this is example of a sequential circuit. So this sequential circuit, you have a combinational adder which just gets a 2-bit value from a register, adds 1, and then when clock goes from 0 to 1, we store value into this state element, which is a 2-bit register. So this is, yeah, now let's go to different slide and go into this thing in a detail. Yeah, so we have 2 flip-flops which form together with other form a counter. So you have register which is a flip-flop. So now let's go into more details. So yeah, so there are like 12 basic ideas of logic design, and once you get these ideas, you can master like all the level to like, complicated level. So it's like gate, area, time delay, parallelism. So you could do multiple parallel things. Then module, which means that you got large design and split it into sub-modules. And the test bench, it's a code which tests designs. Then you have clock, you have reset, you have D flip-flop, which is the element which stores 1 bit during 1 clock cycle. So power, finite state machine, and pipeline. And so here how you build combinational logic. And now in a module you have ports, so you have input and output ports, and you can define your port as a bit vector, and here is a bit vector starting from index 1 to index 0, so 2-bit port. Now you can have a 10-bit LED output, so it's just a vector of values that go like outside of this block. Okay. Now you can do like assignments, so you can write something like a wire, which is like abstract like a wire connection element, and you can put that wire is equal not key 0. So key is a input signal which goes from keys, and we just use some things in wrapper to connect physical pins to this variable key. Okay. Now you can assign to like external LED using such assignments, and here is a special type of logic called the multiplexer, which is a hardware equivalent of if. So basically you are saying here that if signal select is 1, then you get data from 4-bit vector D1, otherwise you get data from 4-bit vector D0. So now you can have like other constants, but we will discuss this like constants later on. So you can have this case, and you have like always block, and there will be always com block, which is a block of combinational logic. So right now our task with this graphics is the following. So what we do is so what we did with this graphics design, we have a VGA controller Sorry, this is not VGA controller. This is actually LCD controller, but this is graphics controller. So which we treat as a black box.
You are not sure with that.
And this is the whole design. Oh, let me change zoom to show this. Zoom. Yeah, zoom is here. Yeah, so this is new share. Yeah. So you see, this is a graphics controller. This graphics controller gives to our logic X and Y coordinates on the screen. So this is current coordinate on the screen. Okay. And yeah. No, a controller produces X and Y for us. Okay. And we need to generate RGB. So controller generates, this is the current X and Y. Right. Controller doesn't need to give X and Y. I mean, like, controller generates X and Y using counters and signs. Yeah. So basically, controller generates counters for current position on the screen.
But I mean, as a module, it should have like inputs and outputs. The output would be X and Y.
Yes, output of the controller X and Y, and input is the clock and reset. Yeah, so input of a controller is the clock and reset, and output is X and Y for us, and then there is the out signals H sync and V sync. So, but those signals user doesn't need to know. So those signals go to VGA display. So all we need to know is that controller gives us X and Y, we need to produce colors. So basically we are saying that we are getting coordinates and we need to compute what colors we are getting for this, what colors we need to put this coordinates. We determine color of something. So combinational logic here, which produces red, green, blue color. This red, green, blue go outside to our display. So now, if you go back to our example here, so we will do examples in VS Code. Let me share VS Code. Close everything not necessary. Yeah. Okay, so what we do is that first we open folder with our examples. Our examples are located in project. Basics graphics music. Yeah, so this is something we see here on the screen. Okay, so we got this red rectangle, and which is inside labs. So let's close everything. Peripherals, boards. So first we go to labs, then we go to graphics. No, let's actually go to Maker Faire, because this is a set of examples we are going to use. Red rectangle, and we can see file called laptop.sv. We have it on the screen. Let's actually close everything here. Yeah, so we do laptop. So this has a module which some ports, but you don't need to look at this module right now. You just need to modify a part which changes our combinational logic, which creates a combinational cloud, and this combinational cloud starts with the coordinates x and y and produces RGB. So red, green, blue. And in this particular LCD, our red channel is 5-bit, green channel is 6-bit, and blue channel is 5-bit again. So those are numbers from 0 to 31, from 0 to 63, and from 0 to 31. So now what we do is that we are saying that if x is more than 100 and x is less than 150, and y is more than 100, y is less than 200, then our color is 30. And this draws this red rectangle. So we go to file and we do open in integrated terminal. Then in this integrated terminal, first you need to choose board. So you need to run script 06, choose another FPGA board. So you do dot slash, then you 06, then press tab. So now it shows you a menu. And in this menu, you need to choose if you don't connect this thing, and you don't connect it yet, you choose a 10 Nano 9K LCD 272 no TM 1638. So this is called here 56. Yeah, so this is called 56. Yeah, okay. Then you run a script called 03. So you do dot slash 03 tab, and you run it. Yeah, if you do this on the Windows, you need to put a bash space script name. Yeah, or you can use bash. Yeah, so now you can see that it. You can see now that it created red thing. Okay. So next, our next exercise is to create. Like our next exercise is to create like 2 rectangles. So now we are doing red and we are doing green, and they like intersect, and on intersection you get yellow color. And our next is rectangle and keys. So what we do is we make color dependent on key. So which means that if you open an integrated terminal, you just run 03 tab, you synthesize. Oh, it's because of two keys. 1 second. Yeah, it just this is like this like project is like constantly under this like is constantly under development. Yeah, because here we're using 3 keys, but on this board we have only 2 keys. You see, so here you have key 0, 1, 2, and key 3. So let's actually put here both key 1 and put here key 1. Okay, and now let's run it again. Yeah, I need to put. So this set is actually supposed to run with this thing connected, but we can connect it later. Okay, so now you can see that we can change color of this rectangle and length by pressing rectangle color and rectangle width by pressing those keys. Okay, so we just press those keys. so now, yeah, I can actually show this here. You can change by pressing key. Oh, wait, I can actually put video. We can change by pressing keys. Yeah. So you can change it by pressing key. Okay, so now how can we make images that like move on the screen? So what we do to make moving images, we create a special structure called counter, like a 10-bit variable, which is actually incremented on every like clock bit. But because our clock is a 50 megahertz, so 50 million times a second, we want to use actually slow. So we have special signal called slow clock. And this slow clock, it actually goes up and down every second. Okay. So now we are making that always when slow clock goes from 0 to 1, then if it's reset, so if you press like reset button, then we set counter to 0. But actually we have power on reset, so this is not relevant for us. But but otherwise counter increases plus 20. Now what we do with our rectangle is that we put if x is less than 150 plus counter. So on every second, this counter increases by 20. So we will see our red rectangle to grow. Yeah, so now
X.
it's
only gonna move.
Yeah, yeah. It
No,
will no, it will not move vertically. It will go its size. So x left will be the same, but right size will go to the right. So now what we do is that we open an integrated terminal and we run same thing ./03. So we synthesize this this design. Yeah, and now you can see that it grows by 20 every second. Okay. Yeah, so now you can modify it so that it moves rather than grow by just adding counter to here, like 100 plus counter, x plus 150. Yeah, by doing this practical exercise, you figure it out. So next thing, what you do is that you can put some block in your design, which is called a strobe generator. And this is just a black box, and you tell it that this is our frequency of clock, which is 50 megahertz. And this is a frequency of strobe, which is 30 hertz. Which means that it simply, so here is our like fast clock, right? So this clock has like 50 megahertz, and then 30 times a second it produces pulse during one clock cycle. So now we can change this 30 times a second. So we will have some smooth movement of the thing. Okay. Now yeah, it's here. So now now we are making counter which is sensitive to regular clock, so to 50 megahertz clock. But we change value of this counter only when pulse is set to 1. So 30 times a second, we increase value by 1. Okay. Now we add this counter to x to both x more than 100 plus this counter and x is less than 150 plus this counter. By doing this, we are creating moving rectangle. But note that because our counter is 10, no, it's like 8 bit. So 8 bit plus is from 0 to 255, right? So this means that once our x, once it reaches 255, this will actually go outside of our like outside of our script. Anyway, let's synthesize it.
Roll over.
Yeah. So now, yeah, you can modify code to roll it over. So now we are doing open integrated terminal, doing 0.3, and we synthesize it. So now, yeah, you can see that it is now moving. You see? So now what we can do next is okay, a rectangle. So now we can have multiple rectangles moving with a slightly different speed. So one is uses counter, twice counter, and another is single counter. And yeah, and then we can moving rectangle and 7-segment display, we can skip it. And we can make it control using keys. So we can control this movement using keys. So all we do to control it using keys, we just create we get pulse, and then we create two counters. One is dy, and another is dx and dy. And now when we when we press key 0, so when we press key 0, we subtract, so we like decrement dx, and when we don't press, it goes plus 1. So we like increment. So we control it by keys. And now in our rectangle, we just add dx and dy. So let's try this, and you can see how we control it using keys. So open integrated terminal, ./03 synthesize. Oh yeah, this has 3 keys, so okay, let's see. We actually put here 7-segment display. We need to comment this out because we are not using 7-segment display. Yeah, if you connect this sync, we use 7-segment display, but let's not use it right now. Shift reach. So does it have anything else here? Or counter? Yes, actually, I need to modify examples to accommodate configuration without TM 16. Okay, so back to file goes in. Okay, while execution. So is there here counter is not deployed. Okay, so we commented out something. 113. Oh, this one. Okay, so we need to put here dx. This is actually a bug. So we can put here dx. Or you can just put here all zeros. So it doesn't matter. Yeah, this is something I need to fix. Yeah, but also you see, we have put like local IDs here. We are putting this counter to this release. Yeah, so you see now we can control using keys. So you see, when we press key, it goes this direction. When we don't press, it goes to different direction. When you press, it goes to another direction. Yeah, so now you can control them using keys. See, so now we are like half there to make a game actually. So you see, we are doing. If you press key, it decrements. If you don't press key, it increments. So this is how we control. So this is how we control. Yeah, this is how we control the thing. Now let's go to this like final thing. So what is the difference of this thing? The difference of this thing is that it also draws different figures. So in order to draw like ellipse, it uses the fact that x square plus y square is less than distance defined square, and x multiply y defines parabola. So this is from like college classes on like analytical geometry, or I think this is now taught in high school as well. But this is from those things. Okay, now let's go here. Okay, so now let's try to synthesize this one. Yeah, so now you can see that you got those like figures like a circle, and you can get hyperbola, and like everything is moving, and you can, and actually okay, oh yeah, like if you press this button, it puts X, like it assigns X to color, so you get this shape. Yeah, so this is like basic information you need to start drawing some moving pictures. And basically our goal is that after some short training, people should be able to create their own games, which use buttons and which use such like moving objects. And then we make a competition, and those who win competition can make their game manufactured. So now you can actually try this yourself. So do you want to try here? Do you want to try there? Huh?
But if I try and download everything to my own laptop, that way I get to do it.
Yeah. So, but what kind of laptop do you have? Windows one. Yeah, you can just follow instructions. Which is instruction on the Verilog Meetup website. Yeah. So if you go to so if you go here, if you click on a new platform for FPGA, and then yeah, and then there is instruction here, like at the end. Here is instruction. So you just use that instruction from here, and you can try to put it on your Windows laptop and yeah, if you have some problems, just shoot email and we will it out. Bring your laptop the text and just like Yuri at Pancho.com. So are you connected in LinkedIn? So you can send link. You have a LinkedIn account.
Yeah.
Yeah. So did you connect in LinkedIn? Okay. So can you like type your? So do you have account on LinkedIn? Do you have account on LinkedIn website? Yeah, you can create one. It's useful to watch technology and science kind of information. Yeah. Okay, so okay. Huh?
Can I take one of the kids home?
Yeah, yes. Закажи give it just a second. Okay, so oh wait. Okay, do you see yourself in the list? Yes, you need to like this one, yeah, okay. Yeah, okay. So, okay. If you have questions about setup, just send me email. Yeah. So let me give you this particular this particular set. So you see, like in order to connect and disconnect, you just put this up. Okay. So now. Yeah.
No, o sea, yo no digo que esto no haga así. Esto es como una posibilidad
Oh. Okay, so just follow instructions, test this kit. So tell next week if you have any problems. So you just like test all this like setup and methodology. Yeah. Also, it's a good idea to in parallel read some like textbook. Like if you get textbook which I like recommend here. Yeah, so if you, for example, read like force chapter of this textbook, which is digital design and computer architecture. Yeah, so this is a good textbook.
Sorry.
Huh?
I'll grab it afterwards.
Yeah. So you can see it on the website. Yes, what is that? Yeah, it's better to. But I can actually show you how this looks. Okay, now. So, there you go. So,
That is the way it is. Move the board. Okay. Okay.
So here you can yeah. Okay, now
Get line from the touch. Trying to get
but you have a bunch of contradictory things. So why and right also for what you can do is what stuff what just so what is the yes yeah this so yes it's have size most yeah, so we have the computation of the four, you're gonna show you some visualize
Ya,
just get this one.
o sea, en alguna parte lo que dices es
Okay, so now
¿Qué cosa?
¿Cómo usar el módulo? Oh, yeah. Okay, so. It's so perfect, like, it's such a nice kid, it's such a good thing, it's like so ready.
Directly plug in.
Don't even put it like, you don't have to. Go,
Ready to fly and start doing things.
no, each sector, no, the user, each sector partner, what is the
Oh, no.
user doing that? It's a lot of work to even choose
It
all these variables.
has been built a lot of Lego places. Now we need to, I am trying to draw what it should be the roadmap from what is the basic things you need to learn, how you manage that, how you start thinking, using them, and a way that you can generate something like the game that you want to build.
You mentioned like 13-year.
Like what?
You mentioned 13-year-olds. Do you really have 13 years old Mexico that will do this?
Well,
Or what age do you target?
I don't know. In this program that we're working is with undergrad people in the fourth semester,
Okay.
four or six, 3 or 4 years. Yeah. But for instance, yesterday the group that we were in the Stanford was a kid of 12 years old doing that.
Okay.
I agree, it's not the general thing, but it's amazing how these the kids are able. The kid was understanding everything.
I'm not saying to eliminate it.
No.
I'm not saying make a requirement.
No, that's a nice goal, but it is not the target goal. It's the initial target goal.
And I think the whole layout is pretty like well documented. I would say like you have the synthesized bash and everything, so you just have to run those. Yeah,
Okay.
it's easy to start with this.
For instance, you have some experience in using these things.
Yeah, I work as an RTL design engineer. So
What should be the shortest path that you would like to see
I
to
think
learn
this
that?
is pretty good. Like because for me it was like yeah, I just went to the coursework and coursework was the only thing that started in undergrad. So if I would have had things in my high school, that would have been pretty helpful.
Yeah.
So I think this is a pretty good.
You are in which degree? You are in engineering?
Yeah, I'm a hardware system.
Which level?
I'm in my first year of work.
First year.
Yeah, so I have a bachelor's in mechanical engineering.
Oh, you already have a little bit of.
I've already programmed an Arduino for like lab equipment that takes time. Very basic stuff.
Yeah, that's quite interesting because the mindset to programming an Arduino and the mindset to do this shifts a lot.
She's driving the GPIO. Not, I'm just posting her GPIO here, I mean, for whatever you're doing.
What it seems that you are finishing reporting of the day. Yeah, okay.
Yeah,
So you're
that's like
finishing
the
reporting.
questions.